All the participants join. All the participants join the session. Saris came. Sir, you start the session, sir.
Okay, I'll start.
Okay, sir.
Okay. Thanks everyone for the second session. So before I proceed, I will tell a small actual detail of a particular competition. So what happens in the world of AI is there is a annual competition. It's called ILV SRC Challenge. So this is basically a challenge for evaluating your latest AI ML deep learning algorithms. And the idea is that the benchmark of any AI program in the world today is measured in terms of being able to work with this particular challenge. The challenge evaluates algorithms for basically image classification and object detection in a very large scale. So what happens is there are some thousands of real world images captured, and they have been labeled with real life objects, like there's a fan, there's a light, there's a road, there's a car, there's a bus, there's a scissor. Several thousands of real life examples have been collected, images, and they have been labeled. And then this challenge was thrown to the world by a professor from Stanford called Professor Fei Li. And they actually have been successful in bringing some sort of a revolution in the world of AI with this challenge. So what has been happening is, over the past nearly decade plus, you have been creating a collection of such large hierarchical database. As I said, Professor Fei Li is the primary owner of this. They started publishing this in 2009, and then from 2010 onwards, this challenge has been on. What happened over initial few years is that they actually used MLP, which is what we studied in the previous session, different kinds of neural networks to solve the challenge of identifying large images correctly with their classes, etc. But it so happened that for consecutively many years, the best of the best neural network architectures were stuck at 74, 75%, like that. They were not moving much forward. I think 70, 72, 73, something like that. But then the thought process of the early neural network researchers was getting nowhere. So they said, how do we give more innovation into neural networks to be able to solve image related problems much better? So that's when three scientists, Jeffrey Hinton, Yoshua Bengio, and Jan LeCun, they worked on converting some of the ideas they've been working in signal processing to change the basic architecture of deep neural network, which is multi-layer perceptron, to yield something which is very focused on images. And that they worked on a couple of years, and ultimately around 2012, they got a major breakthrough when an architecture they worked on called CNN worked like magic, and suddenly they could increase the best algorithm accuracy from 70s to 85, 86%. A jump of 12 to 15% accuracy in just 1 year was considered as a major achievement in the history of AI. And since then, it has been a massive, massive effort. And the idea of working with deep learning as the basis of image processing took center stage. Till then, image processing was primarily done by conventional techniques or machine learning techniques like SVM, based on features you could use like HOG features or RGB features, etc. But with this kind of sudden revolution of a image focused architecture called CNN, these three actually got a revolution in AI, whereby they said that from now on, we will start to create really interesting architectures around CNN. So that popularized the basic deep learning. And what it started to do is it started creating a mindset in AI researchers saying that from now on, our goal should be to reach more and more accuracies in ImageNet. So they've been improving on the CNN, basic CNN, but slightly here and there, more layers, more kind of combinations. And in doing that, what they have done is they have come up to today, it is the latest, I think last year, if you see, it was around 98 or 99% accuracy they have reached. And that's the kind of dramatic transformation CNN has brought to the world of deep learning. First revolution was when multi-layer perceptron was discovered. Second layer is where in 2012 we started CNN to help improve the ImageNet challenge, jump 15% in accuracy. And since then, from 84, 85%, today it's reached 98, 99%. So that much adoption has happened in CNN perspective. So that's the power of CNN. So CNN actually you can think of as the reinvention of the neural network. And while doing that, they also cracked another big problem in the AI world, which is practical applications. The moment they saw deep learning based applications to really large image processing, all different kinds of applications started to emerge from the image world, and beyond that in computer vision, and beyond that in text, etc. And we see that there's a huge revolution that happened in the world of AI. So you can say today there are two versions of AI, the one which is before CNN, one after CNN. So today in any computer vision conference, if you go past before 2012, they used to use conventional techniques, image processing techniques, machine learning techniques, which are based on features. But after that, today hardly there is any paper which is not using deep learning. So that is the power of CNN. And that is what actually happened as the primary intervention in deep learning, as the reason why we had such popular uptake of deep learning as a solution for all your real business problems involving computer vision. So what CNN does is they are again a special case of conventional neural networks or multi-layer perceptrons that work very well when the inputs are images. So convolution neural networks are, you can say, kind of neural networks. So in that sense, they're not outside the neural networks. But in addition to conventional multi-layer perceptron neural networks, they provide some special features which are very good for understanding image patterns. So what the structure of a convolution neural network is, it is adding a couple of conventional multi-layer perceptron kind of layers. On top of that, they add some special layers known as convolutional layers. So in that sense, they're actually somewhat like MLP, but there are some special case with some additional, very focused layers, which are very specific to understanding images. So what you do in typically a convolution neural network is you actually achieve automated feature extraction, which I was talking about at the start, instead of having you to develop artificial input features. With CNN, you actually can extract features from images automatically. So this is the basic CNN architecture. If you see, there are, again, like a conventional multi-layer perceptron, there is an input and there is a output layer. The last layer, for example, if the input is a 28 by 28 image, which is a handwritten character digit, the output will be one of those 9 classes, right? Is it a 0, 1, 2, 3, 4, 5, or up to 9? So what we need to look at is, what is the difference between conventional MLP and CNN? So if you see this particular diagram, let me tell you, this part, which is actually an MLP. This actually talks about a set of hidden layers fully connected from one layer to the other, pretty much like the conventional MLP. And these are what we earlier called dense layers. So dense layers are very much like the conventional multi-layer perceptron, right? Then as we look at other layers in the CNN between input and the MLP layers, they actually occur as a full batch. The way it works is the batch, which is before the MLP, occurs in pairs. So this is one pair, this is another pair. And if you see the pairs occur as combinations of two. The first one is what is called as convolution. The next one is what is called as max pool. So you can decide on any number of combinations of convolution and max pool, between the input layer and the final certain level of MLP layers. That is exactly what CNN does. What CNN does is it adds these combinations of two special layers, convolution and max pool layer, and the architecture may consist of one or many combinations of convolution and max pooling layer. And these combinations of max pooling and convolution layer are basically the ones which are responsible for generalizing the capability of neural networks to handle image specific properties in a seamless manner. So broad architecture, there is input, there is output. Just before the output, there is a bunch of hidden layers, just like in a multi-layer perceptron. But before those dense multi-layer perceptron layers, there are batches of pairs, typically convolution and max pooling combination. So that is the innovation which Hinton Benzio extra brought to the architecture. and worked like magic in improving the ImageNet challenge, going from simple 70% to 85%, today reaching 95, 97, 98, 99%. So what are these two layers? The two layers are convolution and max pooling. I forgot one more thing. Between convolution and max pooling, there is a ReLU function. That is very important. ReLU actually has been a big contributor to the realization of the convolutions. So it is these three combinations: convolution, ReLU, and max pooling. These three are the new innovations which have added to the additional image processing capability of CNNs. Otherwise, CNN is a kind of a feed-forward MLP where data goes from input all the way to the output as a forward layer with no cycles. So both MLP and CNN are feed-forward networks. Namely, feed-forward means data goes from input all the way to output in one direction. The arrows are always in one direction. It's not like there is a cycle that is possible. In the afternoon, when we look at RNN, we'll see that there is a cycle that is possible in the network. Okay. Now let's look at what exactly happens in convolution. In convolution, the operation is a very simple operation. What it does is, it takes an original matrix like the image, and it takes another smaller matrix called as kernel, also known as filter. And the filter or the kernel moves across the whole image and produces a smaller matrix. So, for example, in this case, if the kernel or the filter is this matrix 0, minus 1, 0, minus 1, 5, minus 1, 0, minus 1, 0, and suppose image is also simply 3 by 3, the kernel when applied to image will be place-wise dot product. So 0 into 2, right? If you see here, the way I'll probably use a laser pointer. Okay, see 0 with corresponding position 2. 0 into 2 minus 1 into 2 plus 0 into 2 minus 1 into 2 plus 5 into 3 minus 1 into 2 plus 0 into 2 minus 1 into 2 plus 0 into 2. That is what is meant by applying the kernel on the image. You get one matrix here. But think about, suppose you have a larger image. Suppose you have image like this, a large image. So what you do is you take the kernel, you start moving from the left corner, you get one data. Then again move forward with a stride, again you apply. Again move forward, apply stride till you reach the end. Then you start from next layer in the image. You do again go forward till you reach end to end. So what kernel application on the image does is it reduces the size of the image, and this output is what is called as a feature map. And what the feature map does is it tries to generalize what are the details that are present in each of the image. So the convolution operation is typically application of a kernel on an actual image to produce what is known as a feature map. Here we took the extreme example where both of them are same size. So this 3 by 3 is reduced to 1 by 1 matrix. But let me try. I'm sure there are other examples where we have, convolution in action with feature map. Because so let me see if I have a actual image. So what, as I said, is basically the convolution tries to extract data from, see how it does. You see here, this is what will get you. So if this is the input image and this is the 3x3 filter, see this is the example. See what it is doing. First it starts from leftmost, then goes forward, then goes the next row, next row, next row. So what happened here? Originally the data was 5x5, it has come to 3x3. So in our case, we had 3x3, it came to 1x1. So in general, what we do is we take the kernel, also known as filter, you apply it from the leftmost corner of the image to the rightmost corner, exactly like what you're seeing here. So you get output, which is a feature map, which is of smaller dimension as compared to the original image. So that is the primary convolution operation. So what convolution operation allows you to do is it actually tries to abstract details to such that, suppose there is an overall image of some parrot in one, another one slightly oriented. It tries to abstract generality from there in a smaller feature map, whereby all parrot images are typically converted to similar data. And that is what is the power of CNNs, which actually is able to abstract the general features contained in the image at a higher level as compared to going into finer details of variations between the images. That generalization of the convolution is exactly what is applied in the overall detection of similar objects across multiple images in light variations. So the first operation which is done is what is known as convolution, which what it does, it takes an image, applies the filter and comes up with a feature map, which is a smaller output. So kernel is a matrix that moves over the input data, performs dot product with that subregion and gets the output as a matrix of the dot product. We saw that, right? Now, sometimes it is possible that it is not possible to get good number of coverage with the filter on the image. So then image can be padded on either side, top, bottom, left and right, with zeros, so that you get more coverage of the filters. So that is called as padding, where the original data is padded with one layer here. You see, original data was probably just 4x4, but we've added a padding layer of 0 on all the 4 directions to the image. So what happens with padding is it is usually helpful in getting a better structure of the output as compared to if it is odd and it does not give enough coverage to the filter. So these are slight variations to the convolution where you may want to pad the image. On the other hand, if in the filter here, you see what is happening. After you cover once, it's just moving to the next pixel to cover. So there, by default, the movement of the filter is just 1 to the right. But suppose you want to change it. You want to say that I will add 2 as the stride, means the filter will move 2 buckets to the right rather than just start after the first coverage, start the next layer column. Instead of that, it will start 2 columns after. So by default, stride is 1, right? It is immediately taking the next and covering on. But if stride is 2, after this, it will go to this step, which is the second step, normally with stride equal to 2. So stride defines the amount of movement you want to do to the filter to cover the image. So the two additional features you want to understand when you do convolution is, while convolution allows you to reduce an image to a smaller size feature map using the convolution filter, but sometimes you may want to pad the image with 1 or 2 zeros layers to give better coverage. And the filter also, you can give different strides, not necessarily a one which is the default stride. So the most important part of convolution is this whole idea of take the large data and you try to get some generalized features from that data. That's what actually convolution does. So even if there is slight variation in, say, an image, a cat is facing something else, it will still derive the general feature saying that it's corresponding to cat. That is what convolution power has been discovered as. And the root of how they discovered this is they talked to psychologists and they found out that the way our visual cortex works is very much like this. It first abstracts to a higher level what you see, and then tries to see that, oh, this is also a cat, this is also a cat. So that is the way it starts to think. That's the basis of the convolution operation. So what is a convolution operation? Takes a filter or what we call as a kernel, applies it to the image, either with padding on all sides, with a stride, which you specify. Basically, stride is 1 or multiple. Okay. So convolution achieves you a smaller matrix than the original image, right? That's the basic idea. That's what we call as a feature map. But then, after having applied this, the next layer, which is very important from the perspective of CNN, is, if you remember, we talked about the max pooling layer. What max pooling layer does is, depending on the filter you use, you will further reduce the feature map to a smaller matrix. What does it do? Let us say you have a 2x2 max pool. So what it does is it takes the image, superimposes the 2x2 on it, and finds the maximum in that and converts that here. So in this 7378, 8 is the maximum. Next, in the next one, 5216, the max is 6. 4908, max is 9. In 3945, max is 9. So max pool is further reducing the spatial size of the representation so that it accumulates the features from the feature maps. So the combination of convolution, which is, you can say, the first level operation on the input image, generates a smaller array called as feature map, and then the input images can ever be further reduced using the max pooling operation. And in CNN architecture, you create several combinations of this. You have first convolution max pooling, then again next one, then again, after certain iterations, then whatever is the final output of max pooling you get, you want to just flatten it. Means however number of nodes you get, just flatten it. And then you have multiple MLP layers to create between output and the flattened layer as the output of the final convolution max pool combination. So this is basically the innovation which was done by Benzio and LeCun and Hinton, which said that if you were to get a better image processing network, we should bring in concepts from visual cortex. They tried different operations. Not like everybody knew that convolution plus max pooling would be the perfect architecture. It's not. After a lot of experimentation, they found this to be the perfect architecture. And then they said, let us divide the features into two parts. One is, let us have the MLP, which is the dense layers, derive the global patterns, whereas let us have local patterns in the image discovered by these components of convolution and max pooling layers. So that's what is CNN. CNN is nothing but n number of combinations of convolution and max pooling. Ultimately, you flatten and send the red set of multi-layer perceptrons. This is what is the innovation which was done in this kind of a basic multi-layer perceptron architecture. There's not much more, much less. It is, of course, once everybody is invented, we feel, oh, it's a simple concept, take matrix transformation, just creating a smaller version of it. So that's how you're trying to create. But think about scientists when they're inventing. They're trying different combinations. They're trying different operations, different mathematical operations. And then they came up with this particular architecture. And now to handle the need for ImageNet, which actually got them this particular challenge. This is really a huge approach. Then what happened is, in order for them to work with simple CNN, it was not enough for them to work with just one or two layers of convolution and max pool. So what they did is they actually created a more complex architecture which is like this. So if you look at the basic architecture which won them the 15% increase in accuracy was not a simple CNN like this. It was actually, from the input, there is a convolution, then max pooling, then a convolution, then a max pooling, then again a convolution, then a max pooling, then two fully connected networks, then the final classification layer. So what you need to understand is, while theoretically we say that CNN power is definitely good, but it is not like just having one or two layers in the same format is useful. The architecture which won them the competition in the ImageNet challenge in 2012 was this particular architecture, where they had 11 layers, out of which there were how many? 1, 2, 3, 4, 5 convolution layers, 3 max pool layers, and 3 fully connected multi-layer perceptron fully connected dense layers. So in general, the innovation which people are trying now is what kind of large networks can be created by the combinations of convolutions, max poolings, and fully connected networks, which will scale to handle large images. So today, while the basic invention was the concept of convolution and max pooling, it's not like we just do one or two and then forget it. Today, there are really large architectures which are coming up, which are way beyond AlexNet. So AlexNet was one of the first success stories in using CNNs for large-scale image classification. But today, let me tell you some more. Let's say, for example, let's look at Microsoft's ResNet. So ResNet is a 101 layer output. Similarly, there is something called as VGG19, VGG16, where there is a combination of convolution, max pooling, and ultimately reaching the dense layers. So there are several such layers. So what happens is, in general, in the AlexNet success story, we see that it has led to several such innovations in terms of large scale combinations of convolutions and poolings to be able to create a very powerful large scale network which can handle large number of images. So let's say, for example, look at VGG19 here. So what it does, first it takes image, then do through convolution, then does a pooling, then again does two convolution, then four convolution, pooling, then a pool, then again multiple convolutions, and finally it reaches four fully connected layers. So what you need to look at is, today in the world of convolution neural networks, people don't use simple so let's look at this. Let's say we have this is a typical example of another network. It's called VGG16. So what VGG16 is saying, let's start from input. First convolution, then pooling. Then again convolution, pooling. Then three convolutions, then pooling. Convolution, pooling. Then convolution, then pooling. Then lastly, the dense layers. So what you need to understand is, there's a lot of experimentation, people trying on different combinations of convolutions and poolings and the fully connected at the end to be able to perform actual image classification of the level of ImageNet. Today, this is one of the simpler ones. For example, ResNet has 132 layers. MobileNet has 92 layers. GoogleNet has 500 layers, as we know. AlexNet had only 11 layers, if you saw that, right? So the power of CNN is coming up with the complex, such large pre-trained models which can work on large kinds of examples. So this is the other example. This is the inception. This is called 22-layer inception model. Then we have another model, which is the VGG19. Then recently, there is another one called as efficient net. So what you're seeing is, the purpose of CNN has been to primarily allow the application of convolution and max pool concepts in different numbers to be able to give a large network, ultimately culminating in a fully connected MLP. But the overall power of this has been that it gives a really large power to classifying images by automatically extracting features. You don't need to go and write your feature variables. You directly give inputs and it will create a classifier based on the actual inputs. I'll show you an actual working example. Then it will become clear that I don't see any variable creation. All I give is, these are the classes, these are the images. Okay. So in CNN, there is nothing more. There are only these two things: convolution plus ReLU, then max pooling. So it is just these two innovations and in different combinations, which is giving rise to a really very efficient concepts of hardware which can handle really large image classifications. So you see, there's no new concept. VG16 is basically a collection of different convolution and pooling operations. Mathematically, you know what convolution does, right? Takes an image, gives a feature map, or takes an input image and converts it to a smaller feature map by running the filter on top. Pooling, what it does, it just takes the maximum in that grid, converts it to a smaller array. So it just used different combinations of these pooling and convolution layers, with lastly creating a set of multi-layer perceptron layers in order for us to get to a really working version of a large pre-trained model. And in this context, the current approach in CNN is actually that people are trying to avoid creating their own custom combinations of convolution, pooling, etc. Instead, what this is, since I have these large networks like this VGG16, like Inception, or like say ResNet, which is 132 layer model, which are trained on the large ImageNet collection, why should I need to create my own CNN network? Instead, why don't I reuse these large networks for my classification? That is what is called as transfer learning. What transfer learning does is, in the context of CNN, it takes an already pre-trained large model like what you have seen in these examples and puts them on your data, and you try to get a model out of the pre-trained model itself rather than developing your own version of the model. And that is the reason why today lots of big companies are working on more and more pre-trained models for CNNs rather than their own custom CNNs. And that becomes very, very effective for companies and people like you and me, because a lot of research has gone on into what number of layers, what kind of layers is to be required by some of these big guys who have created these layers. So what are the transfer learning architectures available for you? You can do VGG16, VGG32, Inception, then there is EfficientNet, then MobileNet, then there's ResNet, and you can have DenseNet, lots of different networks available. So today, there's hardly anybody who actually goes and creates his own custom CNN. Of course, there are a lot of people still do if they have really custom images, which are not very common. But otherwise, the CNN model today is take one large pre-trained model like this and apply it to your particular data and see how you can reuse it. You can either use the whole thing or strip off some of the layers and start adding your own layers on top of it, etc. Okay. So what you need to understand is, when you're deploying your CNN, it's not necessary that you will have your own padding, kernel, stride, and max pooling. Instead, you may want to reuse some existing network. Don't worry about this part, but this is what I was telling you in terms of when you give a CNN an image, ultimately you are able to get a final class which tells you what kind of actual character is there. So having said that, let me show you a real world example of where people are using CNN. So I request all of you to open this in your own Can you please run this? So this is basically a basic CNN example. So if you see here, what they've done is, I've said it is a basic input, then I put a convolution layer, a pooling layer, then a convolution layer, pool layer, a convolution layer, a pool layer, and finally I have the softmax, which is depending on number of classes. So what is this doing? This is actually taking, if you see the way the convolution works, it takes the basic image and see what it has done. It has abstracted the details to a level which is basically giving a similar representation for, if you have two images of dogs, the convolution output, which is the feature map, will have very similar kind of output. That is the power of convolution. And that's exactly the secret sauce why convolution is able to act on extracting features and able to recognize the content inside it. So every time you have a convolution layer, what it does is it takes the image of the previous layer and tries to generalize it to more and more generic patterns, which is able to recognize a more general level comparison. So if you have a dog sitting like this, slightly rotated, you should be able to extract features from different features of dogs in the same. So here, if you see, as the CNN architecture tries to work on more and more images, it tries to identify the different test images. As more and more loops of the iterations go on, the accuracy also keeps increasing and more objects are correctly identified. So initially you see there is more red, but as the architecture learns with more and more loops, it improves the identification capability of each of the object. So you see that as we keeping more and more iterations, the more greens are appearing on the different objects. So you see, initially it's not fully confident that this is a truck, but as we go along, you see that it is getting more and more confident that it is probably a truck. So how it works, as you can see, is the combination of convolution and max pooling abstracts details to the next higher level, so that even though there are slight variations in the orientation or slight variations in color, it's still able to understand that both are actually truck images. So that's exactly what is the secret sauce of the CNN, where the convolution plus max pooling has created nothing short of magic. But here we're not using any pre-trained model. We're using our own architecture, where you say that I have con pool, con pool, con pool. Suppose I change my network. Let's say I'm removing this and change the network and rerun it. So what happens is this will again start from scratch. See, I have fewer convolution and max pool layers. But you see what is happening in the max convolution. You take the image, it is abstracting generalization of the image here, which is basically consisting of broad features. So that is where you're getting the generalization. So here you can play around with the convolution pool combinations and look at the programming action. Now, what I want to do is I want to show you a similar program in a Okay, so I want to show you a practical code in TensorFlow for image classification. Okay, so for that, what you need to do is you have to create a training set directory. So here, for example, this is an icon classification where you have different graphical icons which need to be captured. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 categories. And each of them, you try to find images which are like for each. So different categories of images are there. So let me show you the directory so that you're clear that what we're talking about is the way you want to work with this is. So what you do is, if you are to work on any particular image classifier, you have to create training set and test set. In the training set, what you need to do is you need to just take the individual classes. For each class, you create a directory and you put all your images there. Let's say enable disable. This is the icons for that. Let's say you have zoom. This is the icons for that. So what you have is you are basically labeling the images by this method, saying that all the cards images are in the cards directory. All the checkbox images are in the checkbox directory. All the combo box images are in the combo box directory. So there are 11 categories. So same thing you will try to do in the test set also. You'll create test images corresponding to each of the categories. So now you see what is going as input for your CNN. The input that is going on is the training set of data, which is these are the images. For each of this image, this is the class. Based on that, it creates the internal CNN architecture, which you can then use to actually classify real life images. Okay, so let us look at the code. So this is the Keras is a Python deep learning library built on top of TensorFlow. So this is using TensorFlow backend, and we have different libraries for different layers. So what is the concept we're using? We start with first a convolution, then a max pool. Then you just actually I've commented one more combination of convolution and max pool. So I just have one convolution, one max pool. Then I'm flattening. Then I'm just creating the fully connected dense layer with 256, and then I'm trying to compile. Output is the 11 classes, right? So here we just have one convolution and max pooling combination in my program. Though originally we had, but in experimenting, I said this is good enough. So when I compile it, what it does is it says, take the data from training set directory and see how many classes are there. So it says it found from training data 7040 belong to 11 classes. Then one of the things in CNN and network building it does is, while preparing for each batch in each epoch, it also applies it on the test data on seeing how much is it able to correctly classify the test data at that level. So then if you see what it does is, in the first epoch, going through the entire data, it finds that the accuracy of the training data is 0.83. Validation accuracy, which is on test data, is 0.85. Next one, accuracy is 0.96, validation is 0.88. So like that, I said do 20 epochs. And after the 20 epochs, what has happened is it has stopped at 0.9939 as the accuracy for training. Validation accuracy is 98.57, which is quite good. This is a small data set, so we don't have to worry. So if you want to see what is the architecture, it starts from one convolution, then max pooling. Then you flatten it, then you dense it. Don't worry about dropout. Dropout is a way of scaling network. Ultimately, you have the 11-layer output class. Now, the CNN is ready for actual classification. So what I do is I give it different input images. And just to make it clear, if there are 11 classes, right, depending on 0 to 10, I'm giving it a reference saying that, okay, if this particular output is 0, return cards. If it is 3, return enable eligible. So then what I've done is I've taken a PNG, which is a forward icon, and I've run the classifier.predict for that particular test image. So it says that it is found a forward there. Okay. So what we've done here is effectively gotten the trained classifier on training images. And now this is ready to detect any new image and classify it as per your requirement. So what are the steps? First, you start with creating your architecture. Then you read the images. But in doing that, one of the other things which people try to do is in the training data, if you want to create more variety of training data, from the training image itself, you try to create combinations by saying that I will change the basic image with some vertical flip. I'll try to zoom it with some range, 0.1, 0.2, like that. I'll try to shear it, means try to twist it a little bit, so that for training, I get more versatile set of images, not just the images which you have given. And that is one of the big feature which is present in almost all programming paradigms for CNNs, where from the basic image, you try to create different varieties of training data, so that the more training data, more variety of training data you have, the more robust is your actual classifier. So at the end, we actually are not dependent only on the images which are present in this directory. What you do is you take the images and also dynamically create, you also dynamically create different images here. Make sense? So because this is usually takes some time, I didn't want to do that, but I think it won't take too much time. So what this is doing is, as you can see, each epoch, it is slowly improving the test accuracy, because initially test accuracy may not be very high. Training accuracy may reach very high levels very soon, but test accuracy may not be taking that fast. So this is the reason why deep learning takes a lot of time, because the number of epochs it takes to stabilize the test accuracy may be huge. Here I'm doing a very small data set with very simple images, but if you have large realistic images, like the example I gave you was a CFAR, you actually need a lot of GPU power and a really large parallel processing infrastructure to actually carry out training of the CNN on a large set of images. And that's why people actually nowadays follow pre-trained models like VGG or Inception rather than writing their own CNNs. Because another issue is, even though you may write your own CNN, if you don't have enough variety of images, the training may not be very powerful. Convergence to good test accuracy may not be easily achievable. Here, since it is more grayscale images, we got a good coverage. But in general, it's not like you can always be assured of the convergence to a very good set of validation accuracy. But also you need to understand that the more variety of training data you give, the better and more accurate is the model. That's why we are saying that don't restrict yourself to only the data which is present in the training set, but take the training set and convert it into dynamically generated images with slight transformation like shear, rotate, flip. so that those become input for your training also. So this is not going to take much time. So what you see that already there is a good validation accuracy which has reached 95.71. So the advantage of having smaller images, that even with just one layer of convolution and max pooling, see here what the architecture we have. It's a very simple architecture. Where what I've done is I just taken convolution and max pooling. No multiple sets, just one pair. That itself is good enough for this data set. See, accuracy refers to training data. So it's already reached 99 plus. But validation means test accuracy is still around 94, 95, 97. So what for us more important is the validation accuracy, which is on the test data, which is doing for after epoch, because that's what will help you and decide. Because training data anyway, because it is built on the basic training data on which the image classifier is made, I don't have to worry about it. So what is it in your control? In your control is the architecture. How many layers you want to add? How many max pools you want to add? What kind of filter you want to add? You want to add 2 by 2 or 3 by 3 or 1 by 1? What kind of filter you want to add? Those are some things which you can decide and try to provide a different architecture every time. So based on different combinations, you may try to say which one is going to give you the best validation accuracy. Because ultimately, training accuracy will always be reaching very fast, because that's the data on which you're creating your actual model. The test data is where you need to have very good accuracy level. So you see, you have even reached accuracy 1 here in between. It was nearly, training accuracy had reached nearly 100%. Validation accuracy also is reaching good levels. So once it has finished all the 20 epochs, we should be looking at what is the final validation accuracy, which is good, I'm fine. Then otherwise, you might increase epochs or change the architecture, etc. Now let's look at what is the architecture we got. These are the architecture: convolution, max pooling, then flatten, then dense layer, dropout, then the final dense classifier layer. Now let's look at applying it on an image. Let us say forward image you want to see. It's found that it has actually captured it correctly. If you see fwd1.png, this was the image, fwd1.png. Then card1.png was this, right? So it should be classified as cards. Similarly, information icon is this one, right? So this one is captured as information icon. So the corresponding result is 1 here. So this actually shows you the real power of convolution in a real world image classification. Now coming back to what I started out with deep learning, in this particular approach where I just gave data in training set directories, means labeled data, did I write anything? These are the input columns. These are the input features. That is exactly the power of CNN-based deep learning, where it is automatically able to extract the features from raw images and do classification. You're still doing machine learning task of classification, but I have never given any input data. If you remember the morning example, I actually had to give the input data. What is that? GRE, GPA, or rank, right? These are the input features. Whereas here, I don't know what my input features, input columns are. There's no concept of features All I know is this is the input data, out of which it is generating its own corresponding hierarchy of 2 layers of features, one at the convolution layer, next at the global fully connected dense layer. So it has 2 levels of features it's capturing, and combination of that is going to help it decide between any 2 images between corresponding to 2 different icons. So I promised you that deep learning will help you in avoiding by automatically detecting features. Here I've shown you the real example. And in general, in any CNN, the practice is you will look at validation accuracy as a primary metric, and based on that, you will either change number of CNN, convolution max pool layers, or you may want to try to bring a pre-trained model and then add 1 or 2 more layers of your own, so that you have some generic features plus some specific features to your data set. So this is what we wanted to cover when I said CNN, but in general, any place where you have image classification, object detection, or let's see our familiar example of the CIFAR demo. Let's see where it has gone. I'm hoping it must have converged to quite a bit. Yeah. So because it was not getting attention, it stopped doing that. So this is the other application beyond image classification where it tries to locate objects. Object detection is an advanced version of image classification. Okay. So I'll take any questions at this time. Any questions? No questions?
We follow your channel, sir.
Thank you. So I'm just putting my channel. So request all of you to subscribe. Whoever has not subscribed, you can go and click here. Can I use CNN for text analytics? Yes, CNN can be used for text analytics, like document similarity, by extracting features from text and then doing it. Yes, people have done it. We have done it. Actually, we have done document classification using CNN. Definitely, it can be used also. So depending on the problem, if you're doing classification of documents, you can use CNN also there. See, CNN advantage is it is able to extract features from the data. It can be text, it can be audio, it can be thing. So in the afternoon, when we talk about a different class of problems, which is more about sequential problems when we look at RNN. But otherwise, CNN is, yeah, selecting number of columns, it will affect validation accuracy. See, if you have fewer layers, accuracy typically will be smaller. If you are, see, for us, data was very simple. If you have more complex, colorful images, very much variety, so you should have more larger number of convolution layers. Any other questions? See, but hats off to the people who invented this, they must have done a lot of analysis of different kinds of networks, because let me tell you, for a couple of years, the ImageNet challenge was stuck at 70%. They were struggling to improve it. Any amount of changes in machine learning, image processing technique, image pre-processing was not helping. But suddenly comes this new concept of convolution, and it revolutionized the whole idea of ImageNet competition. And today we have a different version of AI itself. It is basically, I can tell you, there is two AIs. One was before AlexNet and after AlexNet. After AlexNet, it is where AI has now become commonplace. We are using in so many different applications using vision, etc. Earlier also we had AI, but it was not so popular. It was not so commonplace because people were struggling with conventional techniques. Any other question? Which mobile predefined model is better? The larger the number of layers, better it is. So try MobileNet, try DenseNet, try ResNet. Okay. So my request is not just you, ask students also to subscribe to this channel. We keep consistently adding a lot of videos on different deep learning models. Any other question? For document similarity, I would not use CNN, extract CNN based features and then do cosine similarity. First, you extract features using convolutions. Then from those features, you should try, see if you can match using cosine similarity. See, use of CNN is to mainly extract the features from anything, either audio or image or any text, anything. Later, what you use it for? You want to use it for classification, then you can perform a classifier. If you're using it for clustering or similarity, you can use distance metric on the features. Okay. Any other question? CNN, that's it, CNN. Image classification in medical domain is also mainly CNN. Any other question? Otherwise, let's break for lunch.
Participants, any other questions? Okay, sir. Thank you. We'll meet again 2:30, sir.
Okay, thank you. Thanks a
Okay,
lot.
sir.
For those of you who have not subscribed, please go ahead and subscribe to the channel. I
Okay, sir.
promise you it will be very knowledgeable. Thank you. So can I
Okay,
log
sir.
off and log in later?
Yes, sir. 2:30 we will join, sir, again.
Okay, I'll log off now.
Okay, sir. All the participants join by 2:30.
Okay, sir. Thank you so much, sir.